We turn now to the subject of concavity, the second derivative test, and graph sketching, or sometimes called curve sketching. If you're following along in the Thomas textbook, this is section 4.4. The first thing we need to do is define what we mean by concavity. Let me put up a picture and the definition. This is what we're talking about when we talk about what's called concavity. That's, by the way, that's an A, concavity. There we go. So Um, so we have the concept of a function being concave up or concave down, and let's start with the picture because that's always the less scary part. What you can see about this curve is that if I look at it on the left side, it appears to be sort of frowny. It's like frowning down. And if I look at it on the right side, it appears to be smiley. It's sort of a bowl. It's sort of a bowl full of water pointing up, whereas this is sort of a dome on top of the food on the left side. That's the one that's pointing down. So this is really the geometric concept that we're trying to get at when we talk about concavity. But as usual, since this is not geometry class, it's calculus class, we're going to try to define this in terms of the objects of calculus that we already know about, which usually, as you've seen, means derivatives. So the definition that we're going to use for concavity is we'll say that if f prime of x, that's the derivative of x, is increasing on an interval, then we say that f is concave up. And conversely, if f prime is decreasing, then we say that f is concave down. I'll get to this last point in a minute, but let's just take a look at what that means. Let's take a look at the tangent slope right here. If we had to eyeball this slope, we'd say that it was about m equals 10. In fact, I'm just going to write down here. I'm going to write an m, although I could just call it f prime. And we're going to say that this is, sorry, that's supposed to be a colon. We're going to say that right about here, the slope is 10. And if we go instead to here, the slope has come down quite a bit. It's still a positive number, but it's 1. Again, this is not precise. I'm just eyeballing what the slope is. And then here, it's just dead flat, so that's going to be a 0. The slope it's a horizontal line. And then here it looks like we have a slope of about, I'm going to call that about a -2. And then here, let's do one more of these. I'm going to call that about a -8. I'm going to put it a little over here. There we go. So what you can see is that the slope is in this part of the graph where the function appears, where the curve appears to be frowning downward. What you can see is that the slope is actually decreasing. We go from a very high slope of 10 down to +1, down to 0, down to -2, and then further down to -8. Over here, it looks like we have a slope of about, I'm going to call that a -1/2. Again, it's just approximate. And this is clearly a 0. And over here, that's where we have about the 1. And up here, that's a really, really steep slope. I'm going to call that a 20. So what you can see is that in the part of the graph that seems to be, I'm going to separate them, in the part of the graph that seems to be smiling upward, let me just write that a little neater, we can see that the slope goes from -1/2 and then upward to 0, further upward to 1, and then further upward to 20. So this is the characteristic of a concave up graph, is that the slope, in other words, the first derivative, the slope of the tangent line, in other words, the first derivative, is increasing as we move to the right. Now, if you notice, there's a point where this changed, where it changed from concave down to concave up. That's what we call a point of inflection, or an inflection point. An inflection point is a place where a graph changes from concave up to concave down, or vice versa. So those are the terms that we need in order to describe concavity, and this is going to form a central part of our analysis of the shape of graphs and curve sketching. It's important to note that concave up and increasing do not mean the same thing. They're different characteristics of the same part of a curve. So here, just to make the point, here on the left, I'm showing a curve that is concave up and increasing. You can see that it's concave up. That's clearly what the shape of the curve is. If I were to do it in terms of the definition, we'd see that we start with a very low slope, and We go over here to a very high slope, so the slope is increasing, or the first derivative of this function is increasing. Here we have a function on the right that's concave down and increasing. The function is clearly still increasing. It clearly still has positive slope tangent lines, and we saw in the last section through the monotone function theorem that that one way to view whether a function is increasing or decreasing is to say is its derivative positive or negative. So clearly the tangent lines have a positive slope. The derivative is positive, the function is increasing, but you can also see from its shape that it's concave down. So these are two just completely different characteristics of the shape of a graph. It's they both relate to the shape. They're both things that we can figure out through what the derivatives are, but they're different. They don't mean the same thing. Just to make this complete, I've put here examples of functions that are concave down and decreasing and concave up and decreasing. So again, it just depends on what the shape is. So when you look at the shape of a curve, you now have to ask not only is it increasing or decreasing, but is it concave up or concave down? Two entirely separate determinations about the same curve. This, by the way, is just an example of what happens, what it looks like when we change from concave up to concave down. So here we have the function y equals x cubed. I think you're mostly familiar with the shape of this curve. This is concave down to the left of the y-axis, and it's concave up to the right of the y-axis. It's increasing on both sides of the x-axis. Clearly, the function is headed upward regardless of which side of the y-axis we're on, but the shape of the curve is such that it's concave down on the left side of the y-axis, concave up on the right side of the y-axis. And of course, this point here, where we change from concave down to concave up, is called an inflection point. So the next topic is that we can use second derivatives to determine where a function is concave up and where it is concave down. This is just a consequence, really, of the definition of concavity and of the fact that we can tell whether any particular curve is increasing or whether any particular function is increasing or decreasing by taking the first derivative of that function. I know that I'm talking about second derivatives, but I'll explain in a minute what I mean by that. So if f double prime, the second derivative of f, is less than 0 on an interval I, then we say that f is concave down on that interval. And if f double prime is greater than 0 on an interval I, then f is concave up on that interval. The thing about this principle is that it just flows naturally from the definition of concavity. Recall that we said that a function was concave up if its first derivative is increasing, and it's concave down if its second derivative is decreasing. So take a look at what we have here. I've just put a concave up function. What we can see is that we have a function where the tangent line goes from there to there. Then we have a flat horizontal tangent, and there, and there. We put in just some lines. So what you can see is that f prime, the slope of the tangent line, here it looks like -10. Then maybe here it's -1. Clearly at the bottom where the tangent is horizontal, it's 0. Then we'll bring it back up to 1 again, and then here is +10. So what you can see is that f prime itself is increasing. It goes from very strongly negative to a little bit negative to 0 to a little bit positive to very positive. So f prime is increasing. You can see is that f prime is increasing. That's the definition of concave up. Well, if f prime is increasing, we know from the work we did in the previous section that means that the derivative of f prime, let me just write these with an x, let's say that f prime of x is increasing. So that means that the derivative of f prime of x must be greater than 0, because that's what it means for f prime to be increasing. Well, normally we write the derivative of the derivative this way. We would say f prime prime of x is greater than 0. So that's what we're really saying, is that in a concave up function, the derivative of f is increasing, and therefore the derivative of f is greater than 0, which we normally write as f double prime. So that's where this principle comes from. I'll just put the principle up again so you can make a note of it.